Once you have a rough idea about the ideal gas equation, which is P times V equals nRT, wherein P is the pressure, V is the volume of the gas, N is the number of moles, and R is the universal gas constant, and T is the temperature in kelvins. What we can do is we can use this equation to arrive at a relationship between the density and molar mass of a gaseous substance. And while the ideal gas equation is not the most accurate description of a gas that you can find, it still provides a really good approximation to the real world behavior. So what we can do, so we need to relate the density and the molar mass. Sorry, there is a molar mass there. So we need to relate the density and the molar mass. So let's denote density by D and molar mass by, let's take capital M. Now, what is the density? So if you had a box which has, let's say, a volume V, let's just take the notation, and the mass of gas that's filled in this is M, and the volume is V, then the density of this gas into consideration, so D will be equal to mass over volume. So mass is M, small m, and that being divided by the volume that you have. And well, now what we can do from here? So molar mass, what is it? Molar mass is the total mass of the gas that you have divided by the number of moles. And we already have those things. We have already captured them. The mass of gas is m, and the number of moles, just taking this n from here, is n. Now we somehow need to take this and incorporate this into this equation. We have to incorporate both into these equations. Now, what you see here is that you have a v in the denominator, you have an n in the denominator here. So let's do some manipulations. What we can do is we can divide both the sides by v. Let's just do that, just to bring v in the denominator. So this equation right here becomes P is equal to nRT divided by v. What else we can do? We can take this n and we can divide both sides by n, by the number of moles. Why we are doing it? Just to bring n in the denominator. And doing so, we will arrive at P over n is equal to RT times 1 over v. What else can we do? So if you see closely, this P over n is equal to P times 1 over n, and this is equal to this, and the only remaining string in this relationship will be the mass of the gas itself. So if you just multiply both sides by the mass, so the LHS gets multiplied by the mass, the RHS gets multiplied by the mass, you arrive at P, the pressure, times mass over the number of moles, that is equal to, this right here is equal to, let's take this mass and multiply it by 1 over v here, so it will be equal to m over capital V times RT. M over n, as you just saw, is just the molar mass, so P, you will get P times the molar mass of the gas is equal to m over v is the density. So instead of m over v, we will just write d, and RT just remains. RT comes from here. And now you arrive at an expression that, given the density of a gas, you can really approximate to its molar mass, or given its molar mass, you can find its density. And it's just another spin-off version of the ideal gas equation, or the combined gas equation. They are both equivalent facts, just different use cases.